Okay, we're going to end this chapter, chapter 10 of conceptual physics, on Kepler's laws of planetary motion. And let me dismiss my image. Here we go. Kepler's laws of planetary motion. Kepler was assistant to the famous astronomer Tycho Brahe. He directed the world's first observatory. Now, Tycho Brahe kept very detailed notes on the movement of the planets, and Kepler used this data um, that Brahe had collected on planetary motion to determine the motion of the planets. Now he was trying to calculate using uh, using his knowledge of the time and assuming circular orbits, and the the um, the measurements were just slightly off, just slightly off. And well, he didn't say, well, that's good enough for government work. No, he wanted to find out why they were off, and he pursued it and pursued it. And he found that the motion of the planets was not circular, but it was elliptical. So it was Kepler that discovered that they were elliptical orbits and not circular. Now you have to understand the eccentricities of the planets are very, very slight. So they are elliptical, but they look pretty much like circles. And it was his calculations of the fact that they were just a little bit off that he kept pursuing it and found that they were ellipses, that the orbits were ellipses. Okay, oops. Okay, the first law, I mean, these are Kepler's laws of planetary motion. The first law, the path of each planet around the sun is an ellipse with the sun at one focus. What's at the other focus? Nothing. It's empty space. Okay, the second law, the line from the sun to any planet sweeps out equal areas of space in equal time intervals. So you'll see this area SCD is a certain area, this shaded area. Well, SAB is the same area. The area size is the same. Why is that? Because at this point, and we'll learn this later, the kinetic energy is very slow. It is low. What is the kinetic energy? It's 1/2 mv squared. So the mass isn't changing. The 1/2 isn't changing. So what's changing? The velocity. And up here, the velocity is moving very slowly. So it only marks this part of the arc. Down here, where the kinetic energy is great, 1/2 mv squared, the v is very fast, so it sweeps out this much. But in an equal time interval, let's say number of days or a month or whatever you want to give it, this area, where's my cursor? There it is. SCD is the same as SAB. Those areas are the same. It's moving fast over here and it's moving slow over here. We'll get to that more uh, in a few slides. Now, the third law is the square of the orbital period of a planet is directly proportional to the cube of the average distance of the planet from the sun for all planets. You got to memorize that. No, just kidding. What is the bottom line? The bottom line is that the further out you are, the slower your orbit is. In other words, our demoted planet, Pluto, which is now a dwarf planet, it's not a true planet. It takes, I forget, it's in 200 and something years, I believe. I'll have to look that up. I should have looked it up before doing this lecture, but I don't remember. But it's in the number of hundreds of years. Where at the opposite end of the spectrum is Mercury. Mercury travels around the sun. I think it's about 3 or 4 times for every one of our years. So Mercury is traveling very quickly around the sun. That's why it's called Mercury. Mercury was the messenger, the fast messenger god in mythology. And so since Mercury traveled so quickly around the sun, they named it Mercury. Excuse me. So the bottom line, third law, the further out you are from the sun, the slower your orbit is. We won't go through any of the calculations. That won't be something that you're required to know. Just the fact that the further out you are, the slower the longer it takes for you to circle the sun. Okay, recall the following. Object in motion possesses kinetic energy due to its motion. Object above the Earth's surface possesses potential energy by virtue of its position. Remember, kinetic energy is the energy of motion. Potential energy is the energy of position. A satellite in orbit possesses both kinetic energy and potential energy. The sum of the kinetic energy and potential energy is constant at all points in the orbit. There is a conservation of energy. The kinetic energy and potential energy is the same at all points in the orbit around the sun for a planet. Okay, for a circular orbit, the potential energy and the kinetic energy and their sum remain constant. You can see there's a centripetal force keeping this in a circular orbit around I'm assuming it's the sun, or maybe it's just a planet. But a circular orbit, the potential energy and the kinetic energy remain constant. So the distance between the satellite and the center of the attracting body does not change. Potential energy is the same everywhere. No component of force acts along the direction of motion. No change in speed and kinetic energy. Which is the direction of force? Well, it's centripetal force, the attraction of the attracting body, pulling it in a circular orbit. Okay, now kinetic in an elliptical orbit, the kinetic and potential energy vary in elliptical orbits. The potential energy is greatest when the satellite is furthest away, the apogee. The potential energy is least when the satellite is closest. So look at the large PE, the large potential energy here, and small kinetic energy. And by contrast, notice the large kinetic energy here and the small potential energy when it's close, when it's at perigee. And at the sides, they're equal. Kinetic energy and potential energy are equal. Kinetic energy is least when the potential energy is the most, and vice versa. At every point in the orbit, sum of kinetic energy and potential energy is the same. So it's this constant exchange, large kinetic energy, small potential energy. Here they're the same, then it's a small kinetic energy, and it's a large potential energy. And then they're the same, and then it just, is a constant exchange. Just like a swinging pendulum exchanges potential energy for kinetic energy to potential energy and back again. We have this cyclic exchange of kinetic energy and potential energy. Okay, when satellite gains altitude and moves against gravitational force, its speed and kinetic energy continually decrease until reaching apogee. After passing apogee, the gravitational force has a positive component in the direction of motion, increasing the speed and kinetic energy. Speed increases until the satellite reaches perigee, and the cycle repeats. This component of force does work on the satellite. Now, I'm referring to this little vector here. One thing to recall for quiz question is farthest away is apogee, closest is perigee. Okay, let's go on. Oops, did I go too far? No, that's it. The first probe to escape the solar system was Pioneer 10, launched from Earth in 1972 when I graduated from high school. I remember it. It was accomplished by directing the probe into the path of oncoming Jupiter. That was intentional. Let it pass by Jupiter, and Jupiter will accelerate it outward towards the edge of the solar system. So that was it's called gravitational assist and it's used often when you swing a satellite near a large planet. You get a gravitational assist that accelerates it to a higher velocity. Okay, when a projectile achieves escape speed from the Earth, it A, forever leaves Earth's gravitational field, B, outruns the influence of Earth's gravity but is never beyond it, C, comes to an eventual stop, returning to Earth at some future time, D, reaches a maximal height and then enters a perpetual orbit. Well, if you look, it says escape speed. And so escape speed, we know it doesn't forever leave the Earth's gravitational field. It weakens, but it outruns the influence of Earth's gravity, but it's never beyond it. Okay, the B outruns the influence of Earth's gravity, but it's never beyond the influence of Earth's gravity. Okay, voyages to the moon, Mars, and beyond begin with launches that exceed the escape speed from Earth. And if I recall correctly, we said it was 8,000 meters per second to maintain a circular orbit. I believe the escape velocity is somewhere about, I think it's 11,000 meters per second to escape Earth's velocity. I'm surprised they didn't put it in the notes. It may be in the text. So, and I think that's it for chapter 10. And we'll stop it there.